Um, let's see. So the topic we have to discuss today is trigonometric integrals, which we also talk about next week on Wednesday after the exam. And these are kind of like integrals, as you can imagine, involving like trigonometric functions. So sines and cosines, secants, tangents. Um, Again, for today, I'll just kind of like do like a smaller piece, which is how to integrate products of sines and cosines. So let me start here. So for today, how to integrate okay. Maybe important. What do we need to remember about sines and cosines for this type of problems? First are derivatives. So the derivative of sine is cosine. The derivative of cosine is negative sine. It kind of goes likewise for, okay, so the integral of sine was negative cosine, and the integral of cosine was sine. And not, well, I guess that these two, like the integrals, we will use them less, but one identity that is actually kind of like very important for this type of problems would be that sine squared plus cosine squared equals 1. So that's actually very useful for this type of problems. So like again, like just recall these ones. So let me start with like kind of like a simple case, which is if you have like the integral of like a power of sine times cosine of x dx. So for like, for example, here m is a positive integer. Well, I guess yeah, it doesn't have to be doesn't have to be an integer, but let's just say here m is not 0. And also not -1, I suppose. But so for example, if you take if you take m to be 3, like it would be like the integral of sine cube of times cosine of x dx. Or if you took or if you yeah, it could also, I guess it could also be a negative number. So if you took like m to be negative 2, then it could be like this would be like the integral of cosine of x divided by sine square of x dx. So like basically almost any power of sine times cosine. Okay. And the reason why this is relatively simple is that only a u sub is needed. So if you make a u sub, which is u equals sine of x, that will give you the correct answer. So let's say if you do u equals sine of x, du equals cosine of x dx, right? And then like what does the antiderivative, well, what does the integral become? It becomes u to the m times du, right? And we know how to integrate this, like again, provided like I guess even m equals, well, no, we do need m to not be zero. So this gives you u to the m plus 1 over m plus 1 plus a constant. And that gives you sine of x to the m plus 1 over m plus 1 plus a constant. Yeah. Oh no, nothing. Wait, right, like this is completely brand new, like not on the exam. Yes, good question. Let me put this not on the first exam. That making sense so far so good. Okay, so again, like this is more like of a warm up because it was like a more like a use up problem. Now a slightly more interesting situation is what happens if you had cosine cubed instead of cosine in the same integral. So this is like a more interesting case. Just also before continuing, kind of to give more like of a bird's eye view of where we're headed. So the idea is to talk about like integration techniques for like I would say like maybe 2 or 3 more classes, and then and I think with integration techniques is that it can be like a black hole of time because you can always come up with a harder integrand that you try to integrate. So we're kind of like just kind of like doing like a survey of certain classic techniques without being like super like exhaustive because you could this like it's never like integrating is like a never ending topic, like you can always come up with like more clever things to try to integrate. So we'll talk about how to integrate trigonometric stuff like between today and next week and Wednesday of next week, and after that we'll kind of like do more like a 180 and switch to something entirely different, which is sequences, which is what will lead us to series and all this other stuff, which I do feel is a bit more interesting. I mean, like as a perspective, because it's like a brand new concept, like whereas integration is kind of fun, but it can be like like it can sometimes feel too specific, because it's like, oh, this particular integrand, whereas like the series stuff is kind of like a new perspective on like, how to approach certain things. So at least we'll have like, um, 2 or 3 more classes about of this sort before we switch gears into something else. Um, oops, let's say. Okay, so the difference now, right, is that when you have a cosine cube, uh, if you try to use the same u sub, right, uh, that doesn't quite work because like the u sub, right, like the u sub would take care of this factor, then the u would take care of a factor of cosine, but then you still have like a cosine squared like left, which is kind of like annoying, you see? And so kind of like the idea here, which is why I mentioned this identity, the idea here is that the sine and cosine are related through their squares, right? So every instance of cosine squared can be replaced in terms of sine, and that kind of like fixes the problem. So, and in fact, I'll write it in a moment. That kind of works as long as like one of the powers is like odd. So, so what we want to do here is use sine squared plus cosine squared equals 1, which in the version I want to write, I'll write it as 1 minus sine square of x. Okay, and so I'll think of this integral as being sine of x to the m times cosine square of x times cosine of x dx. So this is the part that the du's will take care of. And then the other part, like the cosine squared, I can um, I can take care of by doing this replacement, And so if you make u equals sine of x, again, like that, actually the same u sub as before, right? Then what do you get here? You get u to the m 1 minus u squared times du. Oh, let me stop. Give it a chance. Okay, is that making sense? So far, so good. Questions up to this point. And then, like, how do you integrate that? I mean, the easiest thing is to multiply first, right? Like this to distribute. So you can think of this as the integral of u to the m minus u to the m plus 2 du. And each of these is like separately easy to integrate, right? Like, so like this is like the usual power rule. So that's u to the m plus 1 over m plus 1 minus u to the m plus 3 over m plus 3 plus a constant of integration, and then you just use the fact that, u was sine of x. You can write this as sine of x to the m plus 1 over m plus 1 minus sine of x to the m plus 3. Is that okay? Is that making sense? And in fact, that roughly works well, this trick, whenever one of the exponents, at least when one of the exponents is odd, because whenever one of the exponents is odd, you kind of like take either a sine or a cosine to kind of like leave it ready for the u from the u sub, and then the even stuff that you would have left, like you rewrite it, using this like uh identity. So just to kind of like write that down, in fact, if you want to integrate, if you're integrating integrating um with at least one of m and r, then you can always do this trick. You can always do a u sub, which would be either u equals sine of x or u equals cosine of x, depending on which one is like the odd power, and the identity. To do the integration. The thing is, like, of course, in practice, this can become tedious again because, like, in practice, this can be tedious. So won't do this integral, but just to show you why this can become annoying and be tedious. Because, for example, just to do the other one, let's say I had like what cosine of x to the 4 times sine of x to the 7, let's say, dx, right? If at least, again, one of these exponents is odd, so we are good, I'll just break this as sine of x to the 6 times sine of x, okay? And then I will think of sine of x to the 6 as sine of x squared cubed, right? So kind of like sine square of x cubed times sine of x dx. Is that okay? Making sense so far, so good? And hopefully it's already taking shape of where I want this to be headed, because then I write sine squared as 1 minus cosine squared, right? Sorry, 1 minus cosine squared, not 1 minus sine squared. So 1 minus cosine squared. And then if you make a u sub like u equals cosine of x, then the u would be negative sine of x dx. Then you would get u to the 4 times 1 minus u squared cubed, right? Times negative du, I guess. And I mean, and in principle, like, it's once you have it in this at this point, like you can integrate it, but to integrate it, you have to kind of like do the cube first, and then you distribute, which is like kind of like long. So I'm just trying to show you. I just wanted to show you, okay, this could always be done, like to persuade you that this can always be done. But in practice, once you get to something like this, there's like a thing called like the binomial formula that tells you how to like expand these powers up. But like, it's not kind of like our intent. Like usually the powers will be smaller so that, it's kind of like realistic to integrate. But I mean, it can be done, but it just takes a while. So, you know, so this can be integrated, but it's just too long. So it can be integrated, but takes time. But yeah, you would need, takes time because you would need to use uh since it needs I will write the formula. I'll write the identity, but I don't expect you to remember it. There's this identity for a minus b cubed, which is like a cubed minus 3a squared b plus 3ab squared, if okay, minus, I guess, b cubed in this case. But again, you don't need to memorize this one. But I'm just saying, like, that's what you would need to do, because with that, you take a equals 1, b equals u squared, find this out, then distribute, and then you can integrate term by term. But like, you don't have to worry about something that long. That okay? So far, so good, making sense? Okay. And then, so that more or less takes care of the case when like one of the powers is like an odd number. If both happen to be even, this trick does not work, right? Because we had to extract, like a sine or a cosine depending on what you need to make it work. So if both like are even, then you have to use like another trig identity, which is like this like double I guess they're called like what, the double angle formulas. So or like the half angle formulas, like depending on how you I guess, yeah, the half angle, I suppose. So if powers, or both, let's call them exponents. If both exponents are even, uh, you use instead, I'm not necessarily like a big fan where like the problem only relies on an identity which to some extent is obscure, like in the sense like, sine square plus cosine square, then yes, I expect everyone to know that. Like I don't necessarily like have like high expectations that someone would kind of like on the top of their head like remember this identity, right? So for some of these like I would be more inclined to probably providing it, or at least giving you like a hint of how it was supposed to look like, because like it like it's kind of like silly when the problem, like, if you forgot like the sign, it screws everything up. But at least it's kind of, we're discussing right now more like at a theoretical level, what is it that you would use to solve like the problem, and then this is kind of like the identity. Again, this is kind of weird, like, because if we talked about complex numbers at the beginning of the course, which we'll do at the end, ironically, all these identities can be proved in such a nice way using complex numbers, which is very elegant, very beautiful. And it's kind of like annoying that we cannot do this right now. But there will be like a very elegant proof for all these things using complex numbers, which is at least some of them will mention, because they are worth like knowing that they like those proofs are out there. But for now, it just, this identity came from heaven or whatever. Like, it doesn't matter like how we got it. Like, I mean, it's like a very classic trigonometry identity. It's not that it requires complex numbers or anything like that, but it's like there is an elegant proof with complex numbers. But so, for example, just to show you, you know, how, like, let's do this example here. Like, let me, which is the one that I want to use. Like, and let's, yeah, like just to illustrate this, which is kind of like the smallest example to illustrate this, because at least you need both numbers, both powers to be even. And if like if you choose the number to be zero, one of the powers, then you're just either integrating sine square or cosine square, like on their own. So if you want them mixed up, at least one of, they need to start at two, and then already like four and two, like four is already like a very high exponent, like, that it would take an amount of time that we don't want to spend on doing this. So like sine square and cosine square sound like a good, like the sweet spot, like in terms of like showing what the point is about for doing this, but without like being too kind of time consuming. So if you kind of like if you kind of like apply the identities, you get, for sine square you get 1 minus cosine of 2x divided by 2 times 1 plus cosine of 2x divided by 2 dx. Okay. And here, like for the numerator, what you can use, if you remember, is like the difference of square formula that a minus b times a plus b is a squared minus b squared. Okay. But that one is like important to, like that one is like, again, one of those that I do expect you to remember, but if not, you can just like FOIL and you would find it, but it does save you some like amount of time. So if you do that, then the denominator is easy, that's just 4. And then you square 1, that's just 1, and then you square cosine of 2x. Is that okay? Is that making sense? So far, so good. Good. Okay. And then to integrate this, like the first one, like you split you split this into two fractions, right? So this is 1/4 minus cosine square of 2x over 4 dx, right? Okay, so the first one is going to be easy to integrate. Integrating a constant is just like the constant times x. So, and then basically it all boils, I could put like a constant of integration, but I'll put it at the end once we integrate the second one. Um, so it all boils down to how do you integrate cosine square of 2x, right? Um, and for this one, kind of like you apply the same identity again. So it's kind of like a bit recursive if you think about it, because like the idea is like, okay, if you go back to the identity for cosine square of x, right? The way to think about this identity is that it works for any value of x. So think about like, so what this does is relates the square of the cosine with the cosine of twice the angle. So here the angle was x, and the angle here is 2 times x. But if the angle is now 2x, the angle here should be 4x. So it's kind of like, secretly think of like, or call this theta and then put theta equals 2x. Like, if you want to do like a intermediate step. But so what this says is that so cosine squared of 2x is 1 plus cosine of 4x divided by 2. That making sense? And once you have that, then then like this won't be too bad to integrate. So you will have 1/4 of x minus 1/4 of one, like, let's put it here. 1 plus 4 of 1 plus cosine of 4x over 2 dx. And now each one is like not too bad because okay. So like again, like the first one is just integrating a constant with respect to x, that's just x over 2. And then for this one, you just have to do like a u sub, like u equals 4x, for example, like that would work. So if you do u equals 4x, let me put the u sub here. If you do u equals 4x, I mean, then the u will be 4 dx, so you get like an 8. Like, I mean, once you divide by that, you get like an 8. So and an integral of cosine is sine. So you get like after you kind of like do the u sub, you get like something like sine of 4x over 8, right? Usually if you do these u subs in your head, I always recommend like checking like mentally that the derivative works, because sometimes like you can mess up and put the 4 at the top instead of like the bottom, you see, like, and so it's better to just take the derivative to see what you get. So if you take the derivative here, you get sine, sine becomes cosine, so cosine of 4x, perfect. And then by the chain rule, you get an extra factor of 4 that got cancel with one of the 4s here. So, that kind of tells you that you had to put the 4 at the bottom instead of like the top. Okay. And like, since this was like the last integral that we were doing, then yeah, like that, I can put the plus e there, and that is more or less like, uh, well, you can rearrange this a little bit so that it looks better. That okay? Does that make sense? Any questions? Oh, you mean like here, like an x over 8? But the thing is, like, there's a 1/4 of x, right? Oh, sorry, then it should be an x over 8. Yeah, yeah, you're right. Yeah, sorry. Yeah, I now see what you're saying. Thanks. Good. And then, okay, let me do one more example. And then again, like, as I was saying, like, I'll finish so that I can see if you wanted to ask me something specific about the exam. So these are kind of like pairs of like sines with cosines, like, how to deal with sines and cosines. The other two kind of like important pairs for this type of problems are tangent and secant. So the other ones, and I'll just do an example today, and we'll continue it after next Wednesday. Tan with secant. The other important pair is tan with secant. So for that, what do you like again? What do you need to remember in terms of identities involving tangent and secant? First, like the derivatives. The derivative of tangent is secant squared. That's useful, and the derivative of secant is secant times tangent. And then there's kind of like an analog of sine squared plus cosine squared equals 1 for secant and tangent, which you can find by from that identity. So if you take sine squared plus cosine squared equals 1, right? And so for example, if you divide both sides by cosine squared, right? What do you get? You find this also identity, which is useful. So sine squared over cosine squared, that gives you tangent squared, right? And then cosine squared over cosine squared, that gives you 1. So you get the tangent squared plus tangent squared plus 1 and equals 1 over cosine squared, which is secant squared. Okay. Is that making sense? That is actually like, if I never memorized that one, I usually just do that. Like divide both sides by cosine and cosine squared, and then you're good. Like, so you only need to remember sine squared plus cosine squared equals 1. Because again, like kind of if there are formulas that take a few seconds to kind of like rederive, it's better not to like add like extra formulas to like in your head that you are supposed to memorize. So this is kind of like a useful trick to kind of like get it quickly. Okay. And once you do that, then like once you have those identities, like these type of problems are not that different from like the ones that we were doing before with sines and cosines. So again, let me just do this example, and next time I'll continue doing others. But so so here, just to kind of like show you how you would think about this problem. Okay. Like again, the idea is kind of like to rearrange things so that a use up is convenient, right? So if you think about the use up, um, what are the possible use ups that you may try to do? Like just based on this, like you may try to do like u equals tangent or u equals secant, right? So if you wanted to do u equals tangent, you want to kind of like reserve a factor of secant squared for the du. So like you kind of like take out like a secant squared from here, right? Right? So these already would be fine, right? You could take u equals tangent, but then you get this secant of x, and then you're like you stop, right? Because like that's kind of like an annoying, like there's not much you can do here. If you had like a secant squared, right? If you had like a secant squared, then you would be fine, right? Like it would be good. So what I'm trying to say is that here, like again, if you're not sure of which the u sub should be, if you just try like kind of like trial and error, like to work first with tangent, like you kind of like get stopped immediately here because of this annoying factor of secant. So what you in fact, so you go back and you are like, okay, no, actually, let me try to make the u equals secant times tangent. Sorry, just like secant. If you wanted u to be secant, then you need to kind of like reserve a secant tangent. So like, let me go back to step one and just take a secant tangent from like a tangent from the first one and a secant from the second one. So this one won't be. So let me just write that u equals tangent won't be useful. So you kind of go the other way. And so you do, okay, let's just write this as tangent squared secant squared times secant times tangent. Okay. And this will be fine because, okay, so you want to make u equals secant. If you make u equals secant, you get a secant times tangent for this. But then you have to deal with the tangent square. But the tangent square, you can deal with it from here because tangent square is secant square minus one. So let me write that down. So I'll put here secant squared of x minus one times secant square of x times secant of x times tangent of x. Is that making sense? Kind of reasonable questions. So far, so good. How are we doing? Like all these integrals are kind of like clever tricks. Like the first time you see them, you're like, okay, so who thought about this? Like, but like someone did like a few hundred years ago, and then like you just learn it. But like it's not like, of course, like you wouldn't like expect necessarily someone to come with the solution from the top of their head. But like, once you see it, like then you kind of recognize like the strategy. So if you make here u equals secant, du is secant times tangent, so perfect, because then this would become you know what, u squared minus one times u squared times du. And again, to integrate that, that's just u to the 4 minus u squared times du, and then this is just u to the 5/5 minus u cubed over 3 plus a constant. But what was u? U was tangent. So you get tangent of x to the 5/5 minus tangent cubed over 3 plus a constant. Sorry, u was secant. Like, sorry, I was like, this one won't work. Like, so let me cross it out because like I was already looking at the wrong u sub. Okay, so now we're like, let me replace here with secant. Sorry about that. Is that okay? Making sense? Questions about that? Okay, so as I was saying, like for the exam on Monday, we'll be doing class time. Just like go, like pay close attention to the examples we did in class, to the workshop problems, including like the ones from this week, because the ones from this week will be up to integration by parts. I'll post the solutions for those, like for the workshop solutions, like probably on Friday, I guess. Look at those. Like if you look at the 3 workshops that we would have done until now, plus the examples from class, like the exam will be very similar to those things. So like, like it will be very predictable. So now I'll just kind of like go around, see if you wanted to ask me anything specific about like a problem you're stuck with. And if you're good to go, then I'll just see you on Monday. But and also if there's something that comes up, feel free to email me or whatever between now and Monday. But yeah, like I prefer to have some time